Hi, I'm Professor Seth Chandler at the University of Houston Law Center, and this video is on symbolic and numeric optimization. It's part of a series of videos for the course Analytic Methods for Lawyers. Let's start with a look at symbolic optimization, and the concept I want to let you have is something you probably might have noticed, which is that if you're at the top of a mountain, it's flat, if it's a smooth mountain. Or if you're at the bottom of a valley, it's flat. How do we know it's flat? Because if you're at the top of a mountain and it isn't flat, well, then you can go up, so you aren't at the top of the mountain. And if you are at the bottom of a valley and it isn't flat, well, then you can go down. And so where you were wasn't the bottom of the valley. Now, that's a little bit simplistic, and mathematicians delight in finding exceptions to these rules, but it's a good start on finding the top of mountains, because really what we have to do is to see if we can find some sort of expression for the slope of the mountain as a function of the domain of the function, and then try to use algebra or numeric methods to figure out where that slope is 0. So let's start with a simple case. It's a quadratic function, and by a quadratic function I simply mean that the highest power is 2. There it is, f of x, and let's get it into the kernel. We can plot it, and so using our eyeballs we can see, if we can plot it, that it looks like the top might be somewhere around 3. So let's do this. The slope can be defined as the rise of the function divided by the run of the function. So let's compute that ratio. Here's the rise of the function. It's the value of the function at x, and we subtract that from the value of the function at x plus some little value h. And what's the run of the function? Well, it's h. That's the difference between the two domain values. So let's actually compute that for our function here. And this is what we get. We get some expression in x and h. Okay, so now let's see what happens as we shrink h. And in fact, I'm going to show you the sort of fancy way to do that here, but let's just first even do a little experiment. Let's just take this expression here, copy it down, and let's plug in a particular value for x. Let's plug in x is 4. Okay? And now let's let h go from 0.5 to 0.1 in increments of negative 0.1. Okay? And so what you'll see is that as we start to shrink h, our slope starts to change. In fact, now let's do it from 0.05 to 0.01 in smaller increments, and it's getting smaller still, and let's do it in really small increments. And it sure looks like it might be approaching 4. Just a guess. And all right, so let's do this the proper way, though. Let's ask, there's a function in the Wolfram Language limit, which actually computes what happens as you start to shrink. So here's the syntax. You simply have the expression, and here's sort of what the shrinkage goal is. You want the h to go to 0. And when we do that, we get 12 minus 4x. And that, in fact, is an expression for the slope of the function. So that operation is so common that there's a name for it, and it's called the derivative. So just so we're clear, what the derivative is doing in one sense is it is finding the limit of the slope, the rise over run, of the underlying function. Another way to look at it is it's just transforming one function into another function. In Wolfram Language, there's actually a built-in function that lets you compute these derivatives. One is the function d, nice and short. D Here's what we're taking the derivative of, and we're taking it with respect to x. We'll see if we have equations with, or expressions with more than one symbol in them, we're going to have to specify which symbol we want to increment the domain of and see what happens to the function value when we increment the domain. So first argument is the expression to be differentiated. The second is the variable with respect to which we are performing the differentiation. Or if you have an actual function rather than an expression, you can use a built-in function in the Wolfram language, derivative, that will compute the same derivative. So here we have a function, x goes to 100 minus 2 times the quantity negative 3 plus x squared, and we're going to take the derivative of that with respect to the first, and in this case only, argument of the function. And when we execute that, we get back a function object, which is, if you can see, right, this is really the same as negative 4 times negative 3 is 12, and negative 4 times x is negative 4x. So this is the same thing. It's 12 minus 4x, and it's the same thing that we got here. So just different expressions for the same concept. Okay, so what can we do? Now that we have this derivative, we can find the value, we can use algebra to find the value where that slope is 0. So what we're going to say is compute the derivative. When is that equal to 0? Remember, we use equal to set forth equality. If we just use equal, we're going to create havoc because we're doing assignment. And we're going to say solve that expression for x. So if we do this, we get x is equal to 3. And if we eyeball this expression, we can see that, yes, if x is equal to 3, then negative 3 plus 3 is 0, and negative 4 times 0 is 0, and so the slope there is 0. By the way, the answer to this is a list of rules because there might be more than one solution. That's why it is an outer list, and the inner list is because there could, in more complicated settings, be more than one symbol that we're solving for in the algebraic form. But so here we just have one rule that's doubly inside a double list. Okay. We could also, by the way, do the same thing using derivative. Here what we're doing is we're saying, okay, find me the new function that's the derivative function. Apply that to x. When is that equal to 0 for x? And so if I do that, we get the same thing. And by the way, if we have any doubts, we can plug in our maximum into our original function, and we get 100. And if you look, you can see that that does appear to be the maximum value. So our answer here happily corresponds to what our eyes can see. Now, in many instances, you don't actually have to do what I just did. There's you don't have to calculate the derivative and then solve for when the derivative is 0. You can just use a function maximize, or if you need to minimize the function, minimize it. So if I do maximize, it's going to tell me it achieves its maximum at x equals 3, and the value at the maximum is 100. There's a cousin, argmax, which I believe maybe takes a capital there. Yeah, argmax. And that'll just give you the value, the x value at which the function achieves its maximum. This will not always work for more complex functions. You have to be a little careful, but for a very large class of functions, maximize will work just splendidly. I just told you how to get to the top of a mountain using either the calculus plus algebra method or the simple maximize method in Wolfram language. But what if you want to get to the bottom of a valley? What do you do? A couple of ideas. First is to realize that minimizing a function is the same thing as maximizing the negative of a function. So supposing I wanted the minimum of this function here. What I can do is I can just take the negative of that function. I just changed the signs of the 8 and of this polynomial here, and I'll maximize this negative. So I do that here, and it works just fine. But there's also a convenience function, minimize, that saves you the trouble of going through this negation business. So syntax is exactly the same as for maximize. Now let's ratchet up the difficulty a little bit. Supposing we don't want the global maximum of the function. We don't want to get to the very top of the mountain. Maybe we want to get to the maximum of a function subject to some constraint. Like maybe we want to get to the highest point on the mountain that is below 30 degrees latitude. Or maybe we want to get to the lowest point in a valley that is in some township. Okay? So we can do this using Wolfram Language. And here's the syntax. We're going to maximize, and then we have a list. The first element of the list is the expression that we want to maximize, and this works exactly the same as with minimize. And the second is a constraint, or potentially a list of constraints that we want to meet. And then our second argument is simply the variable with respect to which we're seeking to maximize. So it's not much different than the original maximize syntax. It's just that we've added this constraint to it. So supposing I want to find the maximum value of that function f of x, remember f of x is this, subject to the, and remember the plot of it was this, I want to maximize it subject to the constraint. Let's narrow that domain a bit. That x has to be less than 2. Okay? And what we'll see is that actually it's maximized at 2, which corresponds to what we're seeing here. Well, that was a nice story, wasn't it? But let's talk about some occasions on which this calculus plus algebra method doesn't necessarily work. So the first is we've got a piecewise function here, and if we think about the slope of g of x here, it's 1 when x is less than 3, and it is negative 1 when x is greater than 3. And so it's never 0. And so we can try very, very hard to find out the value when the slope is 0, but there isn't one. And yet, there's clearly a maximum. Okay? Sometimes the fact that it is piecewise doesn't mean you can't use calculus. Here's a little function here. I've just drawn a spark line of it, where the slope is 0 at the top of the mountain, even though it's discontinuous. But discontinuities in a function can create some issues. Here's another instance. Imagine we've got a function that is only defined over a certain domain. I'm using the condition pattern restriction that I may have discussed in another video to say that above x equals 2, we don't know what this function is equal to. So what we can, but below 2, it's the same as f of x. So one thing we could try to do is to compute the limit of f of x as h goes to 0, restrict the situation to when x is less than or equal to 2, and we'll use the reduce function, which is a cousin of solve, don't worry why I'm using it, to see if there's any value of x that will satisfy this. And it's going to turn out that there's no value of x which is going to, for which the slope is going to be 0. Now, fortunately, functions like maximize and minimize are smart enough to deal with these mild pathologies, and so it's going to be able to figure out the right answer. Here's another pathology. Here's a function which is our friend of f of x, but we've added a sine wave to it with some amplitude. And so here's the function, here's a picture of it. We can try to find, we can take the limit right here, and we can use reduce. Let's actually do that. You can see it can't do it. That is, it knows what the limit is. That's the limit. But it is unable to figure out when that value is 0. Okay? Now, maximize again comes to the rescue. It is good at using numerical methods, which we'll talk about in a moment, to figure out where this function most likely is actually maximized. And here it does splendidly and does figure out the true maximum value. So far we've looked at optimization of univariate functions, but we can also seek to optimize multivariate functions. Here's an example. We've got a function m of xy, and here's its definition, and I'm going to plot it out. All right, so it's a mountain, and you can see that the heights are colored, or the surface is colored according to its height. So at the top of a mountain, no matter which way you move, it's flat. You can't go up. Why? Because if you could go up, well, then you aren't at the top of the mountain. So one thing we can do is to compute the slope of the mountain in the x direction and in the y direction, and I will leave it as a classic exercise for the reader to figure out why. If we figured it out for the x direction and the y direction, that's all we need to do. So here I'm going to move a little incremental amount h in the x direction and compute the rise, and I'm going to divide that by the amount that I've moved, the run, and I'll take the limit of that expression as h goes to 0, and we see that it's 8 minus 2x minus y. I could have, instead of having done this limit method, I could use the d function as I did before. Really, there's no difference in the syntax. It's just I put the expression here, and I specify which variable I want to take the derivative with respect to, and what direction do I want to move. The little postfix expand here is simply to put the output in a form that happens to match the form produced by limit. I could also move, though, in the y direction, and here you see me doing that. I'm holding x the same, but I'm moving y by a little amount h, and I'm computing the rise if I move h in the y direction over the run, h taking the limit as h goes to 0. And again, rather than using the limit method, I could use the d symbol, which tells the Wolfram kernel to take the symbolic derivative of this expression with respect to y, and then to expand it out, and I get the same thing as I did before. Okay, so at the top of a mountain, really it's likely that if I move in the x direction, I don't go up or down, and if I move in the y direction, I don't go up or down. So we can use algebra to find the values of x and y for which those conditions are true. So I'm setting forth here that the derivative with respect to x has to be equal to 0, and the derivative with respect to y has to be equal to 0, and I'm going to use the solve command to tell Wolfram kernel to do the algebra, since I don't like doing algebra. All right, we could also write this, by the way, using this postfix notation, where we specify a list of derivatives and then use the anonymous function here, solve, to figure out when those conditions apply. Same thing. Finally, we can, just to show you this, what I've done here is to combine two graphics. I've taken our original mountain plot, that was this thing, and I'm going to combine that with the graphics 3D object. I'm going to color the point green. I'm going to say make it reasonably big. And then here's the value. Here's the x value of the point. Here's the y value of the point. And here's the z value of the point. But what are x and y? Well, plug in. Remember, that's what slash dot means. Replace all, plug in from this list of solutions that we have here. Remember, this is mountaintop right here. I'm sorry. Plug in from this list of solutions, although it's exactly the same thing. So all I'm doing is putting a composite graphic together, and I'm basically showing you a way in which Wolfram Language can conveniently integrate algebra and graphics, and you can make a nice picture. And instead of going through all that trouble, we could just use maximize as I do here. So let me introduce some vocabulary, and that is the gradient. The gradient is a list of a function's derivatives with respect to all of its variables. It's kind of a vector of the function's derivatives, and it's often abbreviated grad. And so if I write grad of m of xy with respect to x and y, it's going to give me first the partial derivative in the x direction, and then second the partial derivative in the y direction. And so, again, just another way of writing this is this. What I'm going to do is I'm going to thread the equal, remember equal is the same as double equal, the gradient, and I'm going to set that equal to 0. So if I do that, I get these two conditions, and then, you know what, I'd rather write it this way, actually. I think this is kind of a nicer way to write it. Okay, where I'm doing that threading, and then now I'm saying, hey, you've got those conditions, solve it. And when we do that, we get the solution. We find out for what values of x and y is our derivative 0. All right, but I'll just stick with the code the way I had it. Just as we did constrained optimization on univariate functions, we can do constrained optimization on multivariate functions. Supposing I want to find where is m of xy maximized, but I have two constraints, x plus y I want to be less than or equal to 0, and I want the difference between x and y to be less than or equal to 8. So again, I'm going to, instead of having a single expression here, I'm going to have a list, the first part of which is the expression that I want to maximize, and the second part of which is a list of the constraints that what is it, ampersand is a short form for the logical and. I could have written it, and probably I should have written it this way, since I strive not to introduce short forms before I formally introduce them. That's a little better. And so we can run that, and we can find out that this function is maximized when x is 4 and y is -4. We can visualize this, and this code looks very similar to what we saw before. The only thing I've added is this region function option, and I've specified here's a function, and I'm saying, look, I only want you to plot where those constraints that I showed you before are true. So that's the region function option. And so we get a picture, and if you look very carefully, and maybe we can look at this from above. Okay, hold on a second. I need to move that. We can look at it from above. You can see that that's there, and that value looks to have an x value of something a little greater than 0, maybe like 4, and it has a y value of something less than 0, maybe like -4. All right, we'll put it back in its kind of original, I'll reevaluate, form. Time to look at game theory, which is a perfect application of what we're discussing. So, let's suppose we have two players, player 1 and player 2. They're playing a game. The way the game works is player 1 picks an x value and player 2 picks a y value. Their payoffs are both functions of x and y, but they're different functions. Player 1's payoff is our friend m of xy that we define way up here. Player 2's payoff is this new function n, it's also of xy, and here's the payoff. Okay, as I mentioned, player 1 can only control x and player 2 can only control y. So what we're interested in is there some strategy combination xy that is a mutual best response? That is, given y, player 1 can't improve its position, and given x, player 2 can't improve its position. So let's figure out how to compute this. Let's take the derivative of the m of xy, player 1's payoff function, with respect to its choice variable, its strategy x. We did it. Now, let's take player 2's payoff n, as in Nancy, of xy with respect to its choice variable y, and we'll do that. So, what's required for a value, a point xy, to be a mutual best response? It must be the case that player 1 can't improve its position given y. And that means that that derivative we noted here is 0. And it has to also be true that player 2 can't improve its position given x. So we're going to set these two derivatives, and we're going to solve that expression for x and y. And when we do that, we get this value: x is 26 thirds and y is negative 28 thirds. There's a geometric interpretation of what we did, and let's do this. Let's now, here's our situation where the derivative is 0, and let's solve that for x. So what we're now getting is the optimal x as a function of y. That is, this is player 1's optimal x given player 2's choice of y. That's called a best response line, and we can plot that. Here's how I'm going to do that. We're going to plot it with the x value on the x-axis and the y value on the y-axis. That doesn't seem very creative, but it's a good idea. And we'll do that using parametric plot. Here's our parameter. We're going to let y run from negative 20 to 10, and we're going to let the x value be that best response, and we're going to let the y value just be itself. So there's our plot. We're going to do something similar for the second player. We're going to find, here's the best response for player 2, and we're going to solve that for y. So what this is telling us is, here's your best y for any value of x. Again, I use parametric plot. This time I let x, the player 1's choice, go from negative 10 to 20. Our x value is just x, and our y value is that best response. And so I evaluate that, and we get the green line. And now, all we have to do is combine the two. So I'm going to show the x best response, the y best response, and I'm going to stick a graphic with a point over it showing that mutual best response, which has another name, and that is called a Nash equilibrium. So, a Nash equilibrium was figured out by John Nash. He ultimately received a Nobel Prize in economics for it. He actually did a little more than what I just did, but the essence is here. Some of you may have seen the movie A Beautiful Mind with Russell Crowe, and that tells the early story of John Nash. What's interesting is that he emerged from his schizophrenia many, many years later and had a brief period in which he was back in business. And just as an aside, I got to meet Mr. Nash back in the days when he was completely insane, and I also got to meet him again when he was quite sane at a conference. So let's build on what we've just learned. And here what I want to do is I want to take the payoff to the first player, m, and the payoff to the second player, n. Let's add them up and get the total payoff in the game. For what values of x, y? Well, let's plug in that mutual best response, the Nash equilibrium. When we do that, we get the total reward, the total benefit in society is 96.6667. But what if they actually, player 1 and player 2, actually cared about each other, and they tried to maximize their total wealth, their joint wealth, and later they'll figure out how to divvy up the reward, but they'll play cooperatively. They'll each choose player 1 will choose their x, and player 2 will choose their y, so as to maximize total payoff. So what we're going to do is we're going to say maximize that sum with respect to x and y. When we do that, you'll notice we do get a different value than we did before when we were playing selfishly. And you'll notice that 344 divided by 3 is like, what, 115 or so, whereas the payoff when they played selfishly was only 96. So the key observation is that the selfish maximum, that which would be played if people were just playing for themselves, does not end up resulting in the highest possible reward, which is what Adam Smith, the great economist, thought. Under some circumstances, playing cooperatively can lead to a greater total reward, and if there's a greater total reward, each player can do at least as well as they would under selfish circumstances. Let's just be clear on that last point. If we look at what is m of xy given the selfish potential, they're getting 63. Player 1 is getting 63. If we look at n of xy, given the selfish situation, they are getting 33 1/3. So we have to come up with a solution that gives each of them at least that much, otherwise they will revert to playing selfishly. So we have 344 thirds to play around with if x can be compelled to play 17 thirds and y can be, if player 1 can be compelled to play x as 17 thirds and player 2 can be compelled to play y as negative 19 thirds. Well, let's see if we could do that. If I give, let's say, 210 thirds, which is 70, to x, that leaves, how many thirds left? 134 thirds left for player 2. But if we divide that by, that means that player 2 is going to be getting 44. Player 1 gets 70 and player 2 gets 44. Both are made better off. And so what we might want to do, therefore, is to, instead of commanding somehow, player 1, you must play 17 thirds, and player 2, you must play negative 19 thirds, maybe we'd like to write a law in the form of a function t that takes wealth away from x and gives it to y. That is, t of xy, t being the tort system, says it looks at any values xy, and it says, okay, I'm going to take wealth from y and give it to x. And the question is there a function, t of xy, such that the players, after considering their tort liability, t, will, in the pursuit of their private greed, without the need for further government intervention, be induced to play, player 1 will play, I'm playing 17 thirds, and player 2 will say, well, in that case, I'm playing negative 19 thirds. So the question is, can we alter the payment functions through a wealth-conserving transfer such that the Nash equilibrium also maximizes joint welfare? And what we're going to find out is not only is there such a function, there are an infinite number of such functions that will work in that fashion. And so we might want to, instead of having a command economy, we might want to harness one of the most powerful forces in the universe, human greed, to achieve an efficient result. Let's look at this. Just supposing I pull out of the air the following t function. That's a transfer that's going to take wealth from y and give it to x. Do not ask right now how the heck I got this. But there it is, okay? T of xy. We can plot it just to see what it looks like. There's a picture of it. All right. Now, let's do this. Let's take, here's player one's position. They start with m of xy, but they're getting t of xy. Player two's position is they start with n of xy, but they have to give away t of xy. And now what I want to know is, does it happen to be the case that if I say, what's x's best move here? What's the derivative of this sum with respect to x? And what's player two's best move here? What's the derivative of this difference with respect to y? For what values of x and y, if any, will both those derivatives be 0? And lo and behold, look at that. X is 17/3 and y is negative 19/3. How did I find this function? I'm not going to tell you. Are there any others? Yes. So basically, we just used a combination of calculus and algebra to figure out where functions are maximized. But there are a lot of functions out there in the world where maybe you can compute the derivative, but conventional algebra cannot figure out where the value of that derivative function is 0. Moreover, for a lot of higher dimensional functions, there are a lot of them that have local minima or maxima, and it becomes extremely difficult to use algebra to find a global optimum. Remember, supposing you've got a function that looks like the one I've got here, okay? The slope at the bottom of this valley is 0. The slope at the top of this little foothill is 0, but neither of those are the maximum of the function. It looks like the function's maximized over here. So while the slope being 0 is certainly relevant to a determination of where the global maximum is, it's not all that there is. So let's figure out how to use numerical methods to figure out probably where a function is maximized. And in the real world, probability is what you're going to get. So here's a wavy quadratic function here. What we can do to figure out where the maximum is instead of using maximize, we just stick a little n in front of it. Remember I told you at some point that functions that compute numeric values are kind of like their more rigorous counterparts. You just stick an n in front. Well, this is an example of that. So we're going to maximize s of x with respect to x, and we get a correct answer, which is 1.73. Okay, so we do need to be a little careful in using numeric methods. They are not foolproof. So here's another function, s2 of x, which is our underlying function f of x that we saw a while back. It's at quadratic, but I've superimposed on it a highly oscillatory sine wave. And now let's we can plot this. Right, let's evaluate it. Let's plot it. Okay. And now, if I look at it with my very advanced eyeballs, to me, it looks like it's maximized around there. I don't know, what is that, like 2.5, something like that. Let's use n maximize and try to find the maximum. And if I do that, it gives me 0.559 and the value of 117. And I don't actually think that's right. Let's just do this again, and we will zoom in on, we're just going to zoom in on, say, 0 to 3, and then we'll do all. And it's saying it's about here. Whereas, in fact, let's instead of that, let's have it go from 70 to 125. And you can see this is not the right answer, that there's clearly a higher value up at around 2.7 or so. Here, let's have it go to 130. All right, so n-maximize and numeric methods are not foolproof. You have to use them with some caution. One thing I can do is I can give the n-maximize algorithm some additional freedom, as it were, to explore. This might slow it down a bit, but it's going to explore the whole space better. And when I do it this way, I get an answer that is correct, that is where it is maximized. By the way, to search for a global minimum, and if you look at the documentation for n-maximize and n-minimize, you will see a lot of detail on the methods that can be used. There's an entire tutorial on numeric optimization as well. All right, so here's another function, and we might want to compute the minimum of it. The corresponding function is n-minimize, and as it happens here, it looks like to me we are getting the right answer, but we might want to check. N-maximize and n-minimize work on multidimensional functions. Here's a particularly evil function with lots and lots of local minima, and we can tell it to minimize this function. To me, it looks like it's somewhere around 6.5 maybe, but let's see what it finds. So it's telling me it's negative 1.4 and 5. I actually, in this instance, don't know which is the correct answer. Let's even bump that perturbation scale up some more. And let's see here something. Let's just check something. When I did it with 3, it said the minimum was negative 15. When I do it with 6, it's telling me it's negative 30. And I suspect that might be the correct answer. What this is telling you, though, again, is numeric methods may be your only choice, but you need to use them with considerable care. One additional segment for those who find it interesting, and this is on linear programming. So far, I've basically looked at 3 different methods of optimizing function, one directly using calculus, one using sort of the magical maximize method of Wolfram Language, and a third using n-maximize, which is one of these super functions, as they call it, which bundles up a lot of numerical methods and uses a lot of smarts to figure out which numerical method is most likely to solve the problem. There are many more forms of optimization, however, and there's one that I want to look at here because it's a very powerful one, and it's called linear programming. Linear programming works fantastically well if your problem falls into that domain. So what do you need? You need for the objective function, the thing you're trying to maximize or minimize, to be linear. You need the constraints to be linear. Okay? Once you have that, though, you're in great shape. So let's take this problem. You have a function x plus y, and you want to minimize it. In linear programming, you're always minimizing. So if you have something you want to maximize, just take the negative of it. It's subject to the constraint that x plus 2y is greater than or equal to 3, and 2x minus 4y is greater than or equal to 5. Okay? You'll notice that there's a form to these to these expressions, and that is that something on the left-hand side that involves x's and y's is greater than or equal to some value on the right-hand side. Also, we're going to insist that x and y in these examples be non-negative. Okay, so we could just use minimize on this. That would actually work here. So here's what we would write. We'd have this form where first we set out the expression we're trying to minimize, and then we set forth, wrapped up in an and, a logical and, the constraints that we're subject to. So x plus 2y has to be greater than or equal to 3, 2x minus 4y has to be greater than or equal to 5, and x and y can't be negative. And then our second argument are the variables that we seek to minimize. So we can run that, and works just fine. Okay? But if I start to have 100 variables in my objective function here, as it's known, and 100 constraints that I've written down here, which is not unrealistic in the real world, minimize is going to have a very hard time. And so instead, we're going to use something called linear programming. Let's first write a vector, which if we dot product it with x and y, would give us our objective function. Remember what dot products do? If I say AB dot xy, I get A times x plus B times y, okay? You can think of a dot product as a special case of an inner product. And so for an inner product, it's been a while since I've used this. I'm just going to go peek at the documentation here. Right, okay, splendid. For an inner product, you're going to put the first operation. So what we're doing here is we're multiplying. That's the first operation. Times the first vector is AB, the second vector is XY, and at the end of the day, we are going to plus those all together. So that is it's a general case of an inner product. I could use, I don't know, I'll just be adventurous here. Yeah, that actually works. Okay, so for a true inner product, these functions are arbitrary. For a dot product, though, this is what you mean. First times the elements together pairwise, and then add it all up. All right, so let's figure out what vector dotted with xy will give us our objective function. Well, this is not hard, right? We need 1, 1, because 1, 1 dotted with xy will give us, well, 1 times x is x, and 1 times y is y, and 1x plus 1y is x plus y. So let's call that C, and lest anyone think I might have gotten it wrong, here's a new function we haven't seen before, verification test. You put something on the left-hand side, you put what you hope is output on the right-hand side, and if it works, then you get a nice green checkbox. I'll show you what happens in a moment if you get something wrong. So let's suppose I put, oh, I think that's x plus y plus z. It gives me a very sad x there. All right, now let's write a matrix which, if dot producted with xy, gives us the left-hand side of all of our greater than constraints. So I'm going to say, look, the first constraint is 1x plus 2y. So the row of the matrix is 1, 2. Here it's 2, negative 4. All right? And so that's what my matrix looks like. And again, I can verify that if I take M and dot it with xy, I'm going to get the left-hand side of those constraints. And finally, let's write a vector that has the right-hand side of our greater than constraints. We'll call that B. So now that we're done with that little business, I can just write it as the following. Objective function, left-hand side, right-hand side. And bingo. It gets 11/4 and 1/8, which is exactly what we got up here. Now, I will grant you, I think this is a lot more readable than this whole business. And so you're saying, why are you going through all that? What about a problem with 200,000 variables and 1,000 constraints and doing it in less than a second? Okay? So here's, basically this is my C, this is my M, this is my B, and I'm going to postfix this with absolute timing to see how long this takes. And I'm just running this on, I don't know what this is, like a 2017 laptop. Nothing fantastic. It's a very nice laptop, but it's not like state of the art. And there we go. It can derive an answer. So there is a lot more to linear programming. But I just wanted to let you know that it does exist. There are yet more advanced algorithms. We will actually spend a little time with quadratic optimization at the end of the course when we look at, in fact, you may have seen it already when we looked at a portfolio derivation in the introductory lecture, and that's where we'll see it again in the finance section of this course. Thanks for paying attention for this whole long video, and that's what you need to know about symbolic and numeric optimization.